what I wanted to do in this opening talk, this very brief opening talk, is make sure that a lot of you talked about stability. Well, there are two realms of stability we need to think about, and you need to think about both. It's not like you can divorce yourself from one and think only about the other. There's the colloidal stability of the solution, which is something I talked about earlier today, and then there's the molecular stability. The molecular stability, the big difference between these two is the molecular stability has to do with what goes on within the molecule, and the colloidal stability has to do with what goes on between molecules in the solution. So I'm going to go just give you a very brief talk about molecular chemistry, colloidal chemistry, how we have this dual view of proteins. It's perfectly fine, and we switch between them, but it's, again, very worth your while when you're talking about stability of proteins or thinking about proteins that you keep clear in your mind whether you're talking about an intramolecular stability problem. The protein is unfolding, it exposes its interior, that it has low melting point, things of that sort, and the colloidal stability, when I put it into solution, it tends to find someone else to bind to and comes right out of the solution again. And these all can be understood. The colloidal properties can be understood in terms of proximity energies. And so I'll talk a little bit about that, since that's more my game. One of the things that I want to point out, I've been an editor at JBC, I've been an editor on a number of journals, and I want to emphasize to you, never use these words if the paper's going to come past me. Recruits, there's no such thing as recruiting. There's no long-distance force in biology. A molecule that's standing here, the longest distance it's going to be able to talk is perhaps 1 nanometer away. That's where the interactions stop. So you can't have recruiting going on where you have a come hither, look, this protein, you know, and all of a sudden another molecule comes in. It doesn't work that way. Things are going to work by either by diffusion or diffusion one way or another, different dimensions and so forth. Recognizes, another way of saying binds specifically. Binding we have a nice physical characterization for, and a wonderful infrastructure in terms of ways of characterizing quantitatively what's going on in binding. And wants to is my favorite. You know, this molecule wants to do, well, man, I don't know, it's a little anthropomorphic. When we talk about molecular chemistry, we go back to structure, the various aspects of the structure. We tend to be working with highly purified systems, and we tend to infer mechanisms from structure. It's a very powerful way. We're visual animals. We tend to infer mechanisms on the basis of the structure. But I got to warn you, the electrostatics on structure are very misleading. So when someone tells you they've calculated a charge and they've used the crystal structure, the dipole moment, they use the crystal structure to calculate the dipole moment, they may be correct. They may be also very wrong. And we can use these kinds of structures to address questions about what, but they're not very useful if we're talking about questions in biochemistry, biology, about how do things occur. Things occur because of the interaction between molecules. The how has to do with that. The what has to do with what molecules there, what the structure is doing. So